Hello and welcome. In this video, we'll be discussing how to do a chi-squared goodness of fit test using R. So to start with, I'm going to go on and enter my data, customer dat, from the example that I worked through in our lecture slides. So 93, 110, and 100. This is the observed data that I had. I'm going to do Control Enter, send that over to the right, get that done. All right, so remember the different types of proportions we can get in this case. So I might get a proportion where someone says, hey, I want those equally weighted. So I do a third and a third and a third. And in general, what you would do for equal weighting is if I had like 5 groups, I'd do 1 over 5, 1 over 5, 1 over 5. 5 times. If I had 4 groups, I'd do 1 over 4, 4 times. Here I have 3 groups, I do 1 over 3, 3 times. In my case, though, this isn't actually what the weighting was. That would be a uniform weighting or the same weight for each group. I was actually told that we want to use the cost the money that's given to each department to determine the weights. Of course, I'll say, and I did mention in the lecture slide, sometimes you're just given the percentages. So if you have this, you could just type the percentages if you were given them. But for us, we're given the variable from the cost data. So I'm going to make that data set, cost dat, $150,000, $375,000 and $325,000. And then what I'm going to do is I'm going to calculate the proportion in each group. Now, there's a couple of different ways that you can do this. You can take the values, each of the values, and divide by the total. And remember how we found the total amount of money spent was we added up all of the amount of money spent. So we could take each of those and divide by the sum total of money spent. If I highlight this and hit Control Enter, we can double check that this is 850, and I could just type 850 here if we preferred, but this is a little more general as to how I'd do it if I were given a second variable to create my proportions. These would be the proportions. Another way to do it is to do prop.table cost dat, and this says make a proportion table. So instead of doing the counts, make it in terms of proportions, and it gives the exact same number. I might use that second approach, but you don't have to. You can use any of the approaches. And again, this is only useful if you have something different that you're trying to base it on. Probably a little easier would be, if you're doing the uniform where you just enter in the things in a list. Enter in the proportions in a list that you got. So for me, I'll just copy this into my proportions. And now whenever I need my proportions, I'll just call P. All right, so to build this out, I'm going to need the sample size. That's the sum total of the customer dat. This is the total number of customers that I have, or 303. Remember, to find the expected values, I do the proportions times the total sample size. So my expected values are P times N. My observed values is just that raw data that I have, the customer dat. Oops, and I have a typo, an equal sign there. So I've got my observed, got my expected. And then I go on and I do my my calculation. And actually, I can copy and paste from the test of independence if I had it pulled up. I don't, but remember, it's observed minus expected, quantity squared divided by expected. And again, if I highlight something and do an open parentheses, it wraps it in parentheses. Or you can just do an open and close parentheses. Squared, and then I add them all up. So I copy that, do sum, and then paste inside the sum, and then adds all that up. There we go. This is my test statistic. So I'll save that as TS for test statistic. Now I can just call TS anytime and get my test statistic. All right, for my critical value, I need my degrees of freedom. And you know what? I'm not going to type a variable for degrees of freedom or alpha here. I'll just go on and calculate the critical value, Q chi-squared. The alpha is going to be, was it 0.05 in this case? And again, not divided by 2 or anything. The degrees of freedom is going to be the number of categories, 3 minus 1. I could just type 2, but I'll just leave it as 3 minus 1. And again, we're always doing lower tail equal false for this. My cutoff is 5.9914. Again, my test statistic, TS, is 35. So my cutoff's here. My test statistic is way, way out there. So my test statistic definitely exceeds the critical value. That is, there is enough evidence to reject the null hypothesis. My null hypothesis was that the amount of customers I was getting was proportional to the amount of money I was putting in the departments. And this is saying that that does not appear to be true. I can calculate my p-value real quick. This is the p chi-squared. I give it my test statistic, my degrees of freedom, and again, I didn't make a variable, so I'll just have to retype it, 3 minus 1, and then lower dot tail equals false. I'm going to give very, very, very low p-value. And again, when you see that e -8, that's a good indicator that this is a very small number. That means move the decimal to the left-hand side 8 places. If you want to see it with that done, again, you can use the format command. Format, I open the parentheses and then I paste. And then I do comma, scientific equals false. And so that takes whatever quantity I give it. I just gave it this whole p-value thing. I didn't save it as a new variable. I'm only doing this once. And then I turned off the scientific notation here. And then you can see all the zeros written out. So I started with the decimal here, back 1, 2, 3, 4, 5, 6, 7, 8 places, and that matches perfectly with our interpretation there. So that gives me 1, 2, 3, 4, 5, 6, 7 zeros before the 1. Very, very, very small p-value, way less than alpha, so there's definitely evidence to reject the null hypothesis. That is, it appears that the customers we're getting is not proportional to the amount spending. That is, if you are spending more money on one, you're not necessarily getting more customers from that compared to your other departments. All right, now for the money. Built-in tests. So how do we do the built-in test? Well, it's super duper duper easy. It's the same thing we had before, the chi-squared test. I give it my data, customer dat. I remember that's my observed data. And then I tell it the pre-hypothesized proportions are these proportions that I put into P. So again, if you wanted to make, say, a list of proportions that was 1/3, 1/3, and 1/3. Oh, I need to wrap that in a C open parentheses. You could do that, and then you would just give it to that, and it would run a different test. So that's not what I'm testing. What I'm testing here is in comparison to the cost stat. I got it from the proportion table of the cost stat, which is just the each value divided by the sum of all of the values put together, which was 850. So how much of that $850,000 total budget was each one of these? So I did 150 or 850, etc. Got these percentages, and then I put these in P equals these percentages, or a list of these percentages, and that compares the customer dat to each of these percentages and says, does the customer data fall along the distribution listed in these percentages? In our case, you can see the test statistic from the built-in test matches our test statistic that we calculated. You can see the degrees of freedom matches the degrees of freedom that we put in, and the p-value matches the p-value that we calculated here too. So everything appears to be lining up with what we did by hand. I will say, if you wanted to see where the differences were happening, sometimes I like doing this, just the observed minus expected squared over expected. Remember, I add up all of these components to add to my test statistic, and the bigger my test statistic gets, the more significant the finding. In this case, I can see the biggest contribution, or the biggest difference between my observed data and the hypothesized proportions is coming in this first cell. So if I look at the customer data, this digital marketing is having a way higher observed value than it was expected. It was expected to have 53 people in there. It actually had 93 people in there. So digital marketing is far outperforming the budget it's being given in comparison. And that's the biggest contributor to this significant statistic. So this can be kind of handy if I want to see, like, where is that happening in a chi-squared goodness of fit test. All right, ladies and gentlemen, well, this has been a presentation of how to conduct a chi-squared goodness of fit test using R. And this closes out our chi-squared part of our course. So yeah, I hope you enjoyed it. Chi-squared super duper useful. Again, in chi-squared, we get to deal with stuff where we have categorical outcome variables. It's the only analysis in this course that we'll cover that covers what to do with categorical dependent variables. And so it's just so darn handy to know how to use, because categorical dependent variables come up often. Again, you can always convert continuous data down to categorical data. If you know the analysis to do with it being continuous data, it's recommended that you keep it, because it's not always a good idea. You lose some information when you convert continuous to categorical. But if you don't have any other analytic technique, you can always convert it down. And so while you lose information, you can at least still analyze it. What that ultimately means is that the chi-squared analysis is one of the most flexible analyses that we'll learn in the course, because no matter the data type, you can always convert it into a data type that chi-squared can analyze, the categorical data type. And so that's pretty cool, and one of the reasons I like it. I had an old stats professor who said if you had to pick one analysis to take with you on a desert island, pick the chi-squared, because again, it's just so flexible to be able to use. You can use it with whatever data types you want. You just convert those data to categorical, and then you run the analysis, which is a pretty handy thing. So again, thanks for sticking with me through this lecture and through this video. I appreciate it, and I will look forward to seeing you in the next one.